Thank you, Jenny. So Matthias Katzfuss is an associate professor in the Department of Statistics at Texas A&M University, and his research has been funded by NSF, NASA, NOAA, the Jet Propulsion Laboratory, and Matthias had been awarded an NSF Career Award, a Fulbright Scholarship, and an Early Investigator Award by the ASS section on Statistics and the Environment. So his research frequently applied to environmental problems and satellite remote sensing data includes spatial and spatiotemporal statistics, Gaussian processes, data assimilation, and last but not least, computational statistics for massive data sets. And this last point will be the theme of today's talk, which is entitled Scalable Covariance Approximations for Environmental and Climate Data. And it will discuss how to estimate covariance, so kernel matrices, when the data set is too large for a standard algorithm. So thank you, Matthias Katzfuss, for being with us today.
Yeah, thank you very much for the introduction and the invitation to talk here. Yeah, so this talk is basically based on a collection of different projects and papers with different sets of co-authors, including Joe Guinness at Cornell and some of my grad students here. And I'll try to reference those throughout the talk. I'm going to start with an introduction to Gaussian processes and covariance matrices and the computational issues that arise when we do inference in that setting. And then talk about one particular approximation that can allow us to apply Gaussian processes to very large data sets and essentially approximate covariance matrices by assuming that the inverse Koleski factor is sparse. And then I will talk about some extensions and applications of that basic idea in different settings, including this subsection here, Nonparametric Inference. I will talk briefly about how this might be applied to climate model emulation, which might be of interest to the people here. Okay, so let's start very simple. Let's say we're interested in function estimation. So we have some function of interest here. We have a toy example, but we don't observe the entire function, but instead we just observe it at certain input values or certain locations in space, for example. And then potentially on top of that, our observations might be noisy. And so what we observe then in the end are these black dots here. And from that, we would try to infer what this underlying gray function is, assuming we don't know it. And one way to do that is to use Gaussian processes, which you can think of as probabilistic function estimators, or you can sort of think of it as a prior over functions. And once we've specified this prior distribution, then as we do in other Bayesian inference settings, we condition on the data that we've observed and compute a posterior distribution. And so then we get out a posterior over functions. And that posterior distribution can be summarized in different ways, including, for example, the posterior mean here, if we just want sort of a point estimate, essentially. But we really get a whole distribution, so we can very easily quantify uncertainties based on that, and, for example, compute point-wise intervals like we see here. Here's what the result would look like if we have data without noise. Then, of course, we know much more precisely what the true function is, and our uncertainties will go down a lot and become, the bands here are becoming very narrow. Now, where can we apply Gaussian processes? Basically anywhere where we have a function of interest. So this function of interest could be a time series, or what might be of a lot of interest to people here in the audience, spatial fields. So a function of, say, longitude and latitude, where we would want to do then, for example, spatial prediction or kriging. So kriging is basically just Gaussian process prediction in geostatistics or geoscience. We can also use this in other settings that might not be as relevant here, like computer experiments, more generally for nonlinear regression, classification, machine learning, and model-based optimization. Okay, so Gaussian processes have some very nice properties and features. We've already seen we can use them to gap fill noisy data with natural uncertainty quantification. Another nice feature is that they're essentially non-parametric models. So the more data we have, the more we can learn fine-scale features without having to do anything. Our prior distribution, our assumptions are the same, but we can learn more fine-scale features if we have more data. which is, of course, not the case if we, for example, use something like a linear model. If we assume a linear model, then the best thing we can learn is linear, no matter how much data we get. But with a Gaussian process, it sort of adjusts to how much information there is available in the data that we have. And then another nice feature is if we specify the covariance function, which is essentially one of the parameters in a Gaussian process, if we specify that appropriately, correctly, then we can actually handle functions that have very different behaviors in different parts of the input space. And so we get very flexible function estimation. So here, for example, we have a function that is very rough on the left and then becomes more and more smooth as we go to the right. And our Gaussian process function estimation and the uncertainties adjust to that because we've specified the covariance function to take that into account. So for example, you could have like, different a process that is more smooth over oceans and more rough over land. And if we specify the covariance appropriately, then we can handle that nicely. So despite all of these nice features, Gaussian processes have one big drawback, which is that they're not scalable to large data sets. And that's basically because if we have n data points, n observations, n spatial locations, for example, where we have observations, then we need to work with an n by n covariance matrix of this form. So we have a covariance matrix sigma, which is just basically evaluating a covariance function or kernel function k at all pairs of locations or input values that were observed as I and Sj, ij equal 1 up to n. So we have this n by n covariance matrix, and we have to work with that, and we have to essentially invert it or decompose it. And generally, if we don't make any additional assumptions or approximations, then the time complexity of doing this is cubic in the number of data points. And what that means is that if we have a small data set with a couple thousand data points, maybe, we can do inference very quickly, but then the cost or the time complexity, or sorry, the time that the inference takes grows very quickly as the number of data points increases. So for 100,000, this might already be infeasible, take many, many days, and certainly for 1 million or more observations, we can't really do direct Gaussian process inference. So what we want here basically is methods and approximations that scale linearly, or at least nearly linearly, in the number of data points. Now, of course, this problem has been realized for a long, long time, and there's countless approaches out there to deal with this issue. Here's just a very, 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 very small subset of some of those approaches and some of the categories that I would place them in. So, for example, one idea is to essentially assume that the covariance matrix is low rank or low rank plus diagonal or low rank plus sparse. There's many, many approximations that fall into that framework. Another is to assume that the covariance matrix is sparse in the sense of having a lot of zero entries. And then we can use specialized algorithms and operations that take advantage of the sparsity, of the fact that there's so many entries that are exactly zero. But it turns out that this sparsity assumption on the covariance matrix sort of precludes us in many settings from capturing dependence at longer ranges, longer scales. And so what people have been doing more recently instead is to assume sparsity of the inverse covariance matrix, the precision matrix. And that can work a lot better. But the problem is that even if we have a very sparse precision matrix, that alone is not enough, because we essentially, for most inference, need to compute the Koleski factor or some sort of decomposition of that matrix. And that can introduce a lot of extra non-zeros, even when we start with something very sparse. And so this is also not really scalable to large data sets. And so what we're going to talk about today is an idea introduced by Vecchia in 1988, which is to directly model the Koleski factor of the precision matrix as sparse. And this has the big advantage, of course, that we sort of get the Koleski factor from the beginning, and we don't have to compute it from the precision matrix and have that infill problem. And that allows us to really get very, very good complexities. Okay, now let me talk about the Vecchia approximation as one idea of dealing with these computational issues. I'm seeing some issues with my audio and video. I know if there's a lot of people who have the issue, then maybe let me know, otherwise I'm just going to continue. So here's the general idea of the Vecchia approximation. Assume we have random vector y, y1 up to yn, and let's assume it's normal. So it's sort of, for example, a realization of a Gaussian process. We'll assume the mean is 0 for simplicity, and then we have this covariance matrix sigma that we talked about before. Now, for any random vector, we can always write the joint density as a product of univariate conditional densities, where the ith element conditions on everything that comes before. So basically, y1 up to y1 up to yi minus 1. Yes. Denoting this by h here for the history in this ordering. So this is just an exact decomposition of the joint density. This by itself doesn't help us in any way computationally, but it does motivate this approximation that was proposed by Aldovecchia in 1988, which is to say, let's approximate this true joint density by an approximation of this form here, where we still have a product of conditional densities, but instead of conditioning on everything that comes before, which we have here, we're just going to condition on some subset of that. And we're going to denote the subset of indices here, qi. And we're going to make the additional assumption for simplicity that all of these subsets are at most of some size m, where m might be something like 10, 20, 30, but much, much smaller in most cases than the n, the total sample size. So this m here really is a tuning parameter in this approximation. If we make m very large, then essentially the qi set will become very similar to the hi set, and our approximation becomes similar to the original density. So we get a very high accuracy in the approximation. But the problem is also when m is large, then we have to deal with these very large conditioning sets, and that's very computationally expensive. So both accuracy and computation time increase with m, but we can, the sort of crucial thing here is that in many settings, we can actually get high accuracy even with a very small m, with a very small conditioning set size, due to something called the screening effect. So in that setting, then we have high accuracy and fast computation, both together. Now, when we look at this decomposition here, the ordering of y1 up to yn is completely arbitrary. It doesn't matter at all. This is always exact. But here, this is just an approximation. So the ordering can matter, and it can matter a lot. You know, what we call y1, what we call y2, and so forth is up to us in some sense. And it matters how we do that. So what people used to traditionally do for these vector approximations is coordinate ordering. So we just basically order, let's say here, for example, in this toy example, from bottom to top and left to right. So this is just 10 by 10 points in a 2D spatial field, for example. So we just order from bottom, top, left to right. This is a simple ordering, but it turns out that you can actually get much better approximations by doing something called a maxi-min ordering, which maximizes the minimum distance to points that were already selected, and we sort of go sequentially through. And what that means is practically when we look at the first I locations in the ordering, only the first I, so not all of them, but just some subset, then we get sort of a roughly equidistantly spread set of points over space. We sort of spread out the points as much as we can at any given point in the ordering. And the exact sort of what that means exactly, this maximum ordering and so forth, is it doesn't really matter that much here. All I want to say here is this maximum ordering can be much more accurate than this coordinate ordering, and we'll use that several times throughout the talk. So at least keep that name in mind. And then once we have our ordering, then we have to select conditioning sets, these qi sets. And typically we just use the nearest m previously ordered locations of variables. So here we have m equal to 8, nearest previously ordered in blue, and then the same thing here in the maximum order. We can do more complicated things, but this usually works very well in practice, this nearest neighbor type approach. Okay, now this vector approximation, we've viewed it here from sort of a approximation to the joint density. And we get out here a joint density in the end. And it turns out that joint density is also normal, just now with a different covariance matrix, sigma hat. And we're going to denote by U the inverse Cholesky factor of that sigma hat. Now, we can also view this approximation separately from a matrix approximation perspective. So sort of forget about all this joint density stuff and just say, we have a matrix sigma that we want to approximate. And we're going to say we approximated by minimizing the KL divergence between a normal distribution with that true covariance matrix and a normal distribution with our approximated covariance matrix, as specified through this inverse Cholesky factor U. And it turns out that the U that we get in the Vecchia approximation is actually the optimal sparse triangular matrix under this KL divergence criterion, subject to a sparsity constraint. So we're sort of restricting ourselves here to triangular matrices that have a particular sparsity structure, which essentially has exactly m off, or at most m, I guess, off diagonal non-zeros per column. And those are exactly the entries that correspond to these QI sets that we had in the previous formulation of the Vecchia approximation. So it's sort of interesting that this very, very complicated looking non-convex optimization problem here has a closed form solution, and we can compute this solution in very fast, a linear time in n, specifically order n times m cubed. So the complexity goes up very quickly as a function of m, but as I said, in many settings, we can get away with a very small m and still get a very accurate approximation. And on top of that, this optimization problem is such that the computations for the n columns are embarrassingly parallel. So we can do this completely in parallel, each column, these n columns. And so basically, if we have enough computing power, enough computational nodes, we can actually get some time complexity that's sublinear. Okay, so this was sort of, in some sense, the definition of the Vecchia approximation. Now let's see how well it works in practice. Here's this toy example again from the beginning, when we have data without noise. Here's the exact Gaussian process solution that we want, but can't compute for large data sets because of the computational issues. And here's the Vecchia approximation of that with very small conditioning sets of size 4, m equal to 4. And we can see they're very, very, very similar. And so, this is a very good approximation. But this is just a toy example. We can actually do a little bit of theory here. And I'm going to do a lot of hand waving here. But essentially, if we have Matern type covariance function or exponential covariance function, and we have infill asymptotic, so we have fixed domain, and we get more and more observations in that fixed spatial domain. Under this maximum ordering that I talked about earlier, and some additional regularity conditions, we can essentially get an epsilon accurate approximation in quasi-linear time in n. So we can actually prove that under some regularity conditions that I ignored here. And this is actually the best known complexity for this particular set of, or this particular problem. And in future work, what we're going to try to do is show that we can actually get consistent estimation and prediction for m increasing logarithmically in n. So this is very nice, very slow increase for this conditioning set size n. Okay, in addition to this, this Vecchia framework actually includes many, many existing Gaussian process approximations as special cases, low rank, full scale, multi-resolution approximation, nearest neighbor Gaussian process. All of these are basically just different Vecchia approximations with different ordering and conditioning schemes. We can also use this Vecchia approximation for making predictions. So for example, kriging. So what we have then is basically we have these observations y1 up to yn. And then on top of that, we want to now predict at some other locations. And so we have this yp vector here, y1p up to ynpp. And then we just apply a Vecchia approximation to the joint vector of the actual realizations that we've observed and the things that we're trying to predict. The only thing to watch out for here is to let these variables here, these prediction variables, to actually condition on each other as well. And that way we can even get the joint predictive distribution to be correct or very close to what we're trying to get. And get this very, very nice joint predictive distribution at many different locations joint. Okay, now let's talk about some extensions and applications of this approximation idea, this Vecchia approximation. So the first thing is, we've talked about now here, or seen in this toy example, our approximation works very well when we have no noise. We've directly observed the function of interest. We can get a very accurate Vecchia approximation. Now, what happens if we go to this setting that we had at the beginning where we have data with noise? And in red, you can see what we want. In blue is what we get. And you can see it's not looking very good. The Vecchia approximation is very inaccurate. So the blue lines are very different from the red lines. And this is essentially because this noise destroys the screening effect. It allows us when we condition on things, if they have noise in them, they have less information, and so we need to essentially condition on a lot more things. So the way we could remedy this, of course, would be to use a really large M, but then we have this computational issue again. So we don't want to do that. So what we're going to do instead is we're going to apply Vecchia to the latent Gaussian process realizations without the noise, because we know it works well for that. And then we can get an approximation that is, again, very, very, very accurate. So here the blue and red lines are very close again with a very small n equal to 4. So that's nice. But there's a little bit of a price to, one more thing here. So basically, here's just an illustration. If you look at KL divergence, so basically how accurate things are, as the noise proportion goes up from left to right, if we do latent Vecchia in blue, we can get very good accurate approximations. If we do this response or standard Vecchia that is applied to the noisy observations in red, then this gets sort of worse and worse as we get more and more noise. So what we do then instead, so the latent Vecchia approximation works very well in terms of accuracy, but there is a price to be paid in terms of the computational cost. So basically, we have this issue again that we have to compute a precision matrix, and then we have to do a Cholesky factorization of that, and that can introduce additional non-zeros. It's a higher cost. So in the interest of time, let me just sort of not go through this in detail, but basically what I'm trying to say here is that the red line and the gray lines are very similar. And what that means is that we can actually get almost the same accuracy that we do with this latent Vecchia, with a latent Vecchia that does an additional approximation using an incomplete Cholesky factorization. And so what that means is we can get almost the same accuracy as this very accurate thing that we saw here, but at a computational cost that is as high as the standard Vecchia that didn't work well. So we get the best of both worlds through this additional approximation, which introduces almost no error except maybe a little bit down here. Okay, so basically this sort of, I would say, almost solves the issue. Now I talked a lot about Gaussian here, but we can actually also apply similar ideas in settings where we have non-Gaussian data, specifically data from an exponential family. So this includes binary data, categorical data, counts, right-skewed data using a gamma distribution, and so forth. And the idea is to basically just assume a Gaussian process at a latent level, and then conditional on that Gaussian process, assume some other distribution from an exponential family that can handle these non-Gaussian data types. So here's an example. We have a latent Gaussian process, but what we observe are, for example, binary data, so zeros and ones. And they have this dependence in this input dimension on the x-axis. And yeah, without going into all the details here, let me just sort of talk through the pictures maybe. So, this is clearly non-Gaussian data, these zeros and ones here. So we can't directly apply the stuff that we saw before to that. But it turns out that we can do something like a Laplace approximation Taylor expansion using Newton-Raphson. And it turns out that this is equivalent to just doing the following iterative procedure. We turn the non-Gaussian data into Gaussian pseudodata. So we get something like this here. It looks more Gaussian. And then we can just assume that this is just, again, Gaussian process plus Gaussian noise, which we just saw how to handle. We can do that. And we just have to do this iteratively a couple times where we update what the pseudodata are after every iteration. So basically, we just do the same problem as before, but we just do it a couple times. But this converges very quickly. It's essentially a Newton-Raphson procedure using first and second order derivatives. And so this will give us convergence very quickly. We just have to do the same problem, say 5 times or 10 times or so. But then we can handle the non-Gaussian data in exactly the same way as before. Problem is, this would still be cubic, but now we know how to do that using Vecchia. We can approximate this Gaussian process prediction problems with Gaussian data, Gaussian pseudodata. And then we can get, for example, much better approximations than using a low-rank procedure that's often used in that context. So our Vecchia Laplace procedure here is much more accurate, for example, in terms of the MSE for binary data, Poisson data, gamma data, and other settings as well. For example, if you're interested in analyzing point patterns, this is often done using something called log Gaussian Cox processes that fits also directly into this framework and can get us these very good approximations with this Vecchia Laplace approach. Okay, let me talk a little bit about this non-parametric inference idea. So far, I haven't made this very, very explicit, but essentially what I've assumed so far is that we know what the covariance matrix is that we're trying to approximate. or equivalently that we know what the covariance function is that specifies the entries in that covariance matrix. But now let's assume the setting where we actually want to make non-parametric inference on this covariance matrix sigma. So we don't want to assume some parametric form like an exponential covariance or a Matern covariance or something of that nature, but we just want to, from the data, infer what the non-parametrically what the covariance entries are. If we just directly estimated the entries of sigma, we would, if we have an n by n matrix, we essentially have to estimate order n square parameters. But inspired by this Vecchia approach that we just did, where we have this sparse inverse Cholesky factor, what we're going to do here is we're just going to estimate a near linear number of non-zero entries in this inverse Cholesky factor. So instead of estimating the covariance matrix, we estimate the entries in the Cholesky factor of its inverse and assume many of those entries are exactly zero. And then on top of that, we're going to put Bayesian prior distributions on the non-zero entries in this U and this inverse Cholesky factor that are motivated by this exponential decay of Cholesky entries for many covariance functions that we used in that proof that I talked about toward the beginning with the quasi-linear scaling. So we're going to use this kind of behavior that we know happens for many covariance functions, diffusion type processes, et cetera, to formulate informative Bayesian priors on these non-zero entries to further regularize the problem. And so we end up with, again, a very, very complicated, non-parametric, rich model here. But it turns out, again, that we can actually solve this in closed form in linear time in n, or at least quasi-linear time, depending on what assumptions we make, and in parallel. So again, the entries of the U can be or the columns of U can be estimated or inferred. Posterior distributions can be computed in parallel. And so this can actually be done very, very, very quickly again, despite being very complicated, very flexible, very complex. So one example where we could use this is, for example, in data assimilation. If you have an ensemble count and filter, we have to infer the forecast distribution or forecast covariance matrix so we can make an update. Often people use localization-based approaches. And what we've seen is that this kind of estimation procedure for the forecast covariance matrix can actually improve a lot over such approaches and then do the ensemble count and filter update based on that. Another example where we could use this is climate model emulation, building a stochastic emulator for a climate model. So here's just, again, sort of a toy example. What we did is we looked at mean surface temperature anomalies from the CESM large ensemble project for some control runs. So this is not actually run into the future. We just sort of do some control runs to see if this works at all. And we picked 98 years. So basically, we have an ensemble of 98 samples from some underlying distribution that we're trying to characterize. And specifically, this is a roughly 8,000 dimensional distribution. So we have 8,000 grid points at each of these four things here. And then, as I said, we actually have a total of 98, but I'm only showing four here, four fields that were outputted by this model. And we fit our model, our statistical model, our non-parametric inference to these 98 climate model output data sets. And then we can, for example, simulate from the posterior distribution. And so these on the right here are actually samples from our statistical model. And at least to my untrained eye, the characteristics that we have here on the left are actually also reflected very well on the right in terms of how smooth things are, in what direction the dependence goes. See here much rougher things over land than we have over ocean and things like that, even though this doesn't use any explicit information about whether there's land or ocean, for example. So this is fairly promising. Now, I think I'm supposed to finish in about a minute or two. So let me just maybe say very briefly that there's many other settings where we can use similar ideas, these Vecchia type ideas. Filters over space and time, in computer experiments, when we have highly anisotropic, non-stationary, multivariate settings. So we can sort of extend this in many other ways. And I'll leave it at that for this talk. And then I'll just conclude and say that this Vecchia framework that we've seen can be used for Gaussian process approximations and can lead to almost universal Gaussian process toolbox. So we can do sort of scalable, Gaussian processes without noise, with Gaussian noise, for non-Gaussian data, for computer models, for climate model emulation, non-parametric inference. And in all of those settings, we can essentially guarantee near linear scalability, and we get all this parallelism. So we can actually sort of get, in some sense, complexity that's even faster than linear in the number of data points. And so, yeah, so here's the references for most of what I talked about, and some support from NSF that I want to acknowledge, and that's it. Thank you.
Hey, thank you, Matthias. Reminder, if you have a question, use the raise your hand button, and I can call on you to ask a question, or you can also type your question into the chat box. So I do see a question from Boli. Go ahead.
Very nice talk, Matthias. Thank you. So I have a question about for the vacuum approximation. Does this does this work like the tapering method that capture mainly the local variability or local dependence, but for the long range dependence, do they also kind of like would they also like overlook the long range dependence?
Yeah, I had some trouble understanding, but let me repeat, and hopefully I got the relevant parts. So I think the question was something like, tapering or localization approaches, in some sense, ignore, or in many settings, ignore long-range dependence. Does Vecchia also have that problem? And yeah, so that's one big advantage of the Vecchia approximation, is that it does not target unconditional marginal covariance or dependence, but instead it only looks at ordered conditional dependence. And that means that we can have a very sparse solution and only condition on a very small number of things that are nearby, and still capture long-range dependence. And one sort of maybe nice way of seeing that, sorry, just go through the slides here. In this maximum ordering, early in the maximum ordering, the points are really, really spaced far apart. And then if we condition on previously ordered nearest neighbors, those nearest neighbors are still really far away in space. And so we can really capture that long-range dependence. And then once we condition on those, we go to finer scales of the maximum ordering. We capture more of the fine scale dependence. But then the joint distribution really can capture fine scale and long range dependence, even if M is very small or we have a very sparse solution. One sort of special case where this is especially obvious is if we look at exponential covariance function on the real line, on a one-dimensional space, where we can get an exact approximation, even with M equal to 2, say, depending on how we choose the conditioning sets, no matter how large the range parameter in this exponential covariance function is. And so basically, yeah, this is just sort of one example where you can show exactly that we can capture arbitrarily like long-range dependence in the sense of the range parameter being arbitrarily large, exactly, even with an extremely sparse solution.
Okay, thank you.
Okay, any other questions? I know Amy Braverman, do you want to ask your question?
Yeah, I have, I think I have two questions. One is sort of specific and the other is more general. The specific one was the latent Vecchia. Did I understand correctly that that amounts to kind of doing some kind of quick initial fit?
No, it's all like a joint model. I don't have a good, a good formula here that I can point to, but it's basically, in some sense, what we're doing is you can think of it in the sense of, so I have my y1 up to yn, which are my, say, latent Gaussian process realizations at the n locations where I have observations. And then I have another vector, say, z1 up to zn, which are the corresponding noisy observations. Now, basically, I have a vector of length 2n when I put them together, half of which is actually observed, the other half is latent. But I can model their joint distribution. And what we're essentially doing is we're applying a Vecchia approximation to this joint big vector. So there's no pre-fitting or anything. It's sort of a joint model to this entire set of 2n random variables, half of which are observed.
Where did you get do you simply not have the latent instances?
No, we don't. So the way I think the nicest way to think about it, or the clearest way to think about it, is to just say, okay, those 2n random variables, I can put them in a vector, and that vector has a 2n by 2n covariance matrix. And what we're doing is we're approximating that big covariance matrix using the vector approximation. So I wouldn't focus too much on like the actual Gaussian process realizations that we haven't observed that are latent. Just sort of forget about those. Let's just say we have a big covariance matrix, and we're approximating that covariance matrix. So we don't need to know the actual values. We're just looking at the covariances.
Right. I'm not clear on is you have the observations for n of those. What information do you have about the other n?
Well, again, I don't need to know what they are exactly. I just need to know what, basically, I have this vector of, yeah, let's put it this way. I have this big covariance matrix, 2n by 2n. I just need to know what each entry of that covariance matrix is. So I don't need all of the entries, but I need to evaluate certain entries of it to actually compute the vector approximation. So that's what I mean. And then, of course, when I want to make posterior inference, I actually need to see the n observations. But I can sort of integrate out the latent stuff once I have.
But you must be making some assumption then somewhere.
Yeah. So as I said, all of the until I talked about nonparametric inference really was under the assumption that I have a covariance function, and I want to sort of approximate the corresponding covariance matrix. And I didn't talk about this here in detail, but of course, the covariance function can depend on parameters, and I can make inference on those parameters using this vector approximation as well. But skip over that in the interest of sort of keeping it fairly high level. But yeah, basically, if you have a covariance function of interest and you know it up to a certain number of, smallish number of parameters, you can apply this. That's the assumption, yes.
Okay. So my other question was a bit more general, which is you did show a nice example of how you might use this to understand to specify the probabilistic structure of an ensemble of model runs, for example. How did you have other specific uses of this kind of technique in mind? And if so, what are they?
Well, I mean, the direct uses that I have in mind are the two that I mentioned, which are climate model emulation and data assimilation settings. So basically anywhere where you have data assimilation, where you would use an ensemble Kalman filter, or we could use an ensemble Kalman filter. This could be used to improve the ensemble Kalman filter and be used within that to estimate the forecast covariance. Now, there are some other settings. I'm working with some people at Los Alamos, for example, and we haven't really started any of this specific other work, but we have some ideas for how one could apply this, for example, in the setting of they have these cyber physical systems and they want to detect anomalies. And so we could use this to essentially make inference on the distribution under a normal setting. And then when we have deviations from that, when there are anomalies, there's sort of some intrusion into the system or whatever, to keep it very general, we can detect that that's sort of outside of what we would expect, for example. But you could also use it in, I mean, I think we've talked about some material science applications, and basically anywhere where you have to infer a dependent structure, ideally from some ensemble, which I would say there's probably lots of settings, and I can only mention a couple here specifically, but I'm sure there's many, many more. You could use this kind of approach in principle with some changes in the detail depending on the application, but I didn't talk about those details here anyway. So.
Right. So I guess I'm thinking of the computer experiments world, and that is what a climate model is, certainly, is a computer experiment.
Yes.
Any idea what kind of, and I'm just thinking out loud, so forgive me if this turns out not to be a good question, but in order to fit an emulator for a climate model, you have to have some training data to do it, but the climate model, running the climate models themselves can be computationally very expensive.
Yes.
Is there a way that the additional power of this method could relieve that burden that you can see?
Well, so I mean, certainly what it would allow us to do is, instead of, say, producing 200 ensemble members from this climate model.
Mhm.
Maybe we can only produce 50 or 80 or 100 or whatever, some subset of that, and then fit our statistical model to it, and then produce additional samples like I did here that have sort of the same characteristics, and then do whatever you wanted to do with the ensemble based on this mixed ensemble of actual climate model output and statistical model output.
Oh, that's interesting.
And then, of course, I mean, this is sort of a very crude way of doing things, but you can summarize this distribution in different ways. Of course, you could look at, what's kind of dependence that the model would say we have between temperature here and stratospheric warming there. Or, I don't know. I'm not a climate expert, but yeah, certain things that might be of interest.
Right. So you also, I'm sorry, I'm going to give somebody else a chance to say something, but I have one more question.
Yeah, I think you're part of this specific working group later also, right?
Yes,
so
yes.
Maybe we'll save it.
Yeah.
Okay, so we have a couple more minutes for this open discussion. Noah, do you want to go ahead and ask your question?
Yeah, I had a couple. First question, like, what's the largest data set in terms of number of samples you've tried this on?
This specific Vecchia approximation that I talked about, maybe 2 million or so. But there are some specific other settings. What is this? Here, for example, with this multi-resolution filter, which is just a special case of Vecchia. So in a space-only setting, we've applied it to maybe 60 million or so.
Okay, thanks. And like, what's the wall time on inference, I guess, just to make it pretty.
Yeah, so it'll really depend on the setting, but I mean, you can sort of say pretty precisely what the actual number of flops is that you need to do. You basically need to compute n, which is your number of data points, times, you need to compute n Cholesky factorizations of matrices of size m by m. And so, let's say you have m equal to 20, so you have sort of n times 20 by 20 matrices that you have to decompose. So you can say pretty precisely what the number of flops is. Now, what the actual time is that it takes to do this would very much depend on, how many computational nodes you have, how much you can parallelize this, how much power, what the actual m is that you've chosen, and so forth. But I mean, in this 2 million setting, this was in a computer experiment setting that we did some computer model emulation. It would be maybe to fit the model in the sense of optimizing over, say, 12 hyperparameters, and then making actual predictions at, say, 100,000 other input locations. This would take on the order of 10 to 15 minutes on my very basic $200 desktop computer here.
Okay, thanks. And then,
Syria,
thanks for that.
Yeah, go ahead.
Second question was just memory requirements. That's another, kind of important cost for doing things, especially for if you envision this kind of algorithm happening online in a climate model.
Right. So yeah, I mean, basically,
can you forget samples?
Sorry, say that again.
I'm just wondering, can you forget samples? Can you use the Vecchia approximation to say, well, I don't want to store these gazillion useless samples in memory anymore? Is that a approach that you can take?
So it's not itself sort of it doesn't reduce the number of data points that you're looking at. So certainly you could do that and just fit it on a subsample or something. But in itself, it doesn't reduce the sort of the dimension or the rank. So it's a full rank type approximation. So basically, if you have n data points, you're going to have to sort of, unless you subsample it, you have to run it, n problems, n little problems. But as I said, it is very embarrassingly parallel, at least in certain settings. And so if you have enough parallel computing power, distributed computing power, you can certainly distribute it very nicely. And the cost is, again, sort of n times m by m matrices. So m can be very small. So in principle, this can be scaled very much over many computing nodes. But we don't have a good implementation that does it right now. But it probably wouldn't be very difficult for somebody who knows how to do these things.
Yeah, thanks for that. Yeah, sounds great for data assimilation.
Yeah.
Right, I think that will end our public section of this webinar. So thank you to everyone who's joined, and thank you, Matthias, for presenting. We will meet again in 2 weeks with a presentation from Ryan Swiver of University of Illinois. His talk is entitled Influence of Uncertainties on the Tails of Climate Projections.